Joining our webinar today. My name is Ashley Stromack, and I am a Customer Engagement Specialist for Test Oil. We are very pleased to be hosting this webinar today titled How to Outsmart Varnish and Avoid Unexpected Downtime. Before we start the webinar, I wanted to let everyone know that you will be on mute during the presentation. We're recording this webinar so I can share it with you later, and by keeping everyone on mute, we'll ensure a high-quality recording. If you have any questions, you can submit them using the questions field in the GoToWebinar toolbar. If we have time at the end of the webinar, we'll address your questions. And if we don't, we can address all of those through email. Okay, let's get started. Today's presenter is Michael Barrett. He is our Vice President of Sales and Marketing. Mike has worked at Test Oil for 23 years in a variety of positions. He's seen the company grow from 3 employees to 50. He led Test Oil's effort into researching varnish 10 years ago and ultimately developing a solution for helping our customers understand varnish potential in their equipment. Today, he is responsible for directing Test Oil's marketing and sales effort. He has personally reviewed and accepted over 3,000 oil analysis reports in his tenure with Test Oil. He helped design an expert system rule for assessing and evaluating lubricant and machine condition. He has spoken at conferences on the subject of oil analysis. In a sales capacity, Mike works closely with customers, helping them develop successful oil analysis programs. Mike has earned a BA in economics from Kenyon College and a master's degree in business administration from Case Western Reserve University. Thank you for joining us today, Mike, and I'm going to pass the controls over for you now.
Ashley, thank you very much. Can you hear me?
Yes, I can.
Okay, we'll get started. Thank you, everybody, for joining the Test Oil webinar series this morning or this afternoon, whichever case may be for you. It has been quite some time that I've talked about varnish. As Ashley mentioned, we got into this varnish issue probably about 10 years ago, and it still is a big issue for our customers today. I think the varnish testing we perform on a monthly basis for our customers now exceeds about 150 samples every single month and approaching 200 samples a month. So that is a pretty good indicator that varnish still is a problem that many of you may have out in your plants, and hopefully today you'll gain some information on a little bit about what varnish is and how it can be detected. I think really what I'm going to focus on today is review some of the precursor conditions that lead to varnish formation and potentially the role oil analysis has in alerting you as owners of critical equipment the potential risk involved. I don't know. I've been into a lot of plants, but I don't know if there is a failure condition that I've seen that can disrupt an operation more quickly than varnish. And for those of you who've never experienced it, you are lucky, because I have seen it firsthand what it can do to turbines and hydraulic systems, and it is a devastating effect. So I always like to start with this, and I could talk for a couple hours on varnish because I can be very passionate about it, because our journey was a 2-3 year journey into varnish, and I can still remember it was probably about 10 years ago walking into a power plant, and they had been a customer probably for about 8-9 years, and we're doing routine analysis on their reports, and they'd send us probably 10, 11 samples every single year from their turbines, and we had never ever seen any issue on the oil analysis reports. And yet the day I'm there, he pulls me out and shows me, walks me out in the plant and says, what is this stuff in my sump? And I mean, I had never seen anything like it. It was this brownish material that seemed kind of sticky, and I said, you know what, it's got a varnish texture to it, but I'm not sure why it's there or how it got there. And that was really, for me, a eye-opening experience into what varnish was all about, because it was clear we were not picking that up on any of our routine oil analysis reports. So I think from a a goal from us at that point was, what can we do from a testing standpoint to somehow quantify these submicron particles that were leading to varnish. The story, I mean, it is an involved story that can go on, half hour, and I think a couple years ago I told this story, and it was an elaborate story, but where we first began with the whole varnish issue goes back to a gentleman by the name of Dr. Sasaki, who used to work for, and I think he just retired, he worked for Cleantech, and he did a ton of work on this colorimetric analysis, looking at this varnish issue by analyzing the color of a patch. So that sort of became, the benchmark in the industry around varnish is this idea of if you can run a sample through a patch and analyze the color with some sort of colorimetric device, that would give you an indication of varnish. And it was the darker the patch, the more varnish. And that was a lot of research on our part to figure out how exactly that works. And then along the way, we met a gentleman down at the old Saturn plant in Spring Hill, Tennessee, who was doing a lot of work with ultracentrifuge on his hydraulic systems, and he was experiencing varnish on his big hydraulic units down in the auto plant down there in Tennessee, and he had implemented a ultracentrifuge to pull out these submicron particles that were not being picked up in his routine analysis. And we, kind of then started to incorporate ultracentrifuge into our varnish package because that seemed to make sense. And then even further, General Electric started to recommend this idea of microscopic particle counting analysis. And for a while, probably for the first couple of years, we were actually making a patch and had this special microscope to manually count particles. And we separate the patch into different grids, and you would count particles in grids, and it was a very tedious process, but again, it was something General Electric had recommended on gas turbines, so that became part of our repertoire, if you will, of trying to isolate these particles and give our customers a better understanding of where they're coming from. So, we did a lot of things like that, and I could go in and tell you great stories about some of the problems we had, but eventually we came out with a report that we have today that is sort of a all-inclusive report that gives our analysts as much information and data as possible to tell our customers if they think they are going to be experiencing a varnish problem. So, that's the background on how we got involved, and it is a very abbreviated background. And as we went forward with varnish, these are, and whoever out there has had varnish experience knows exactly what I'm talking about, but, we would get our pictures like this from customers saying, hey, you know what, I'm going to report back, and this is what I have in my system, yet you're telling me nothing's wrong. So what we were trying to do, excuse me, they want to know exactly what this stuff was. I mean, they'd see things like this on their components, these deposits, and they would call us and say, hey, you know what is this stuff? So, that was sort of the rise of our varnish journey. And, today now, varnish is very well recognized. ASTM, as a matter of fact, even has a definition for varnish. And this is what ASTM defines as varnish. So it's, it's a pretty generic, I would say, definition, but it is exactly what we see when we get pictures from customers, or when we get filters from customers, or when we get baggies of material from customers. This is exactly what we get in those baggies. So where exactly does varnish come from? And while that, the description that ASTM defines as varnish is a good description, I think what you find in most cases, varnish is actually degraded lubricant, believe it or not. It can be comprised of both degraded base stock and degraded additives. And it's usually brought on by increase in heat. Some sort of thermal event causes an increase in the oxidation. It could be brought on by water. Water is a problem that can increase the rate of oxidation. And in some cases, contamination can increase the rate of oxidation. So, in a sense, what's happening is you're introducing some variable into the oil that is increasing the rate of oxidation that will eventually lead to varnish. And I've used this sort of analogy, probably going back to the start, is that oil becomes saturated with these partially soluble soft contaminants, and as the oil cools, these contaminants come out of solution, they agglomerate, they bind together, and then they form this varnish. And if you think of putting sugar in your coffee, this is the best analogy I could come up with, but when your coffee's hot, you put a teaspoon of sugar in your coffee, you stir it, and if you had a glass coffee cup, you wouldn't see any sugar sitting at the bottom of the coffee cup. But as that coffee cools and you stop any sort of agitation with the coffee, eventually what you're going to see is that sugar fall out of the coffee and it'll be sitting at the bottom of the coffee cup. So it's the same sort of issue we have with varnish. And that's, I guess, a good idea why. So we come upon our first trivia question of the morning. And it's a pretty straightforward question, but like Ashley said, I've been with Insight Test Oil for 23 years, and 15 years ago, 12 years ago, I didn't see any varnish, didn't hear of varnish. But why all of a sudden now did the varnish pop up? Here is a very simplistic explanation, but it really has to do with oil formulations, going from a Group 1 base stock to Group 2 base stocks, and even Group 3 base stocks, is that the newer formulations are much more refined, and they're less polar, and they're less able to dissolve these varnished particles. So essentially what happens is these particles in the newer base stocks can't stay in solution as well. The Group 1 base stocks would hold those particles in solution and they wouldn't fall out and you wouldn't get the varnish. So that, coupled with the fact that today's equipment in your plant runs a lot hotter, runs a lot faster, you guys are under the gun to make more, produce more, so there's a lot more stress put on the lubricant through heat, which can result in degradation and contribute to this varnishing issue. So that's kind of the explanation for varnish, and I mean, from our standpoint, it makes sense. It's definitely what we've seen in the last 10 years from both the wear and tear on the equipment and the change in formulations have led to this varnish issue. So these are some of the ideas, or not ideas, sort of the pictures we get from customers, and what happens with the varnish. And it's there's a lot of bad things that can happen with the varnish. And when we got into this, we would get pictures and we would get filters like this, and customers would ask, why doesn't the oil analysis give me any warning that I have a problem? And it's really because of the standard oil analysis tests, the ICP analysis you guys may run, or the viscosity, or the particle counts. None of those tests can give any sort of indication of the presence of varnish or the varnish precursors. there's really no way to predict varnish based on that testing. And I guess that's one of the key issues that I want to stress today is, who's ever doing oil analysis out there, your routine analysis won't pick up varnish. So what do we do? From a customer standpoint, from your standpoint, you're out there running equipment, and you may have a sense that you have varnished. Typically what I've seen is that the customer tells us they got a varnish issue before our report tells them, because the routine will never going to tell them they have varnish issue, and yet they can see it in their systems. So I think the key really is just to make sure you're performing the testing that will capture and quantify the varnish. And that really is a focus of what we're going to talk about today. There's obviously a lot of labs doing varnish testing, and what I want to talk about really is the testing that gets done to quantify these varnish particles, and there's different ways to do it. And from our standpoint is what we've put together is sort of this all-inclusive package that looks at different tests to isolate these varnish particles and give you some sense of how am I doing with varnish. It's by no means the only way to do this, but it's the way we do it. And what I want to do is walk through some of these tests, and then I have some example reports that I think will really give you some understanding of how difficult this is to figure out if there is varnish in the system. So obviously over the last 10 years, since we've been isolating and trying to predict varnish, there's been a lot of change and advances in technology. And a couple years ago is when we rolled out our report that looks at more testing to provide this comprehensive evaluation of varnish potential. And what I want to do is just take a look at the report. No, it's not in no way a method. I don't want to try to sell you this report, but a lot of the testing we're doing is for varnish, and it helps give you a better understanding of what testing you should be doing. So really what we do is on the first page of the report, we've at the top right-hand corner is going to give you a varnish potential rating, and it's typically normal, at risk, marginal, and critical. There's going to be a whole section that lists some sample information. The equipment type is listed. What we really do varnish on is either a turbine, a hydraulic unit, or a compressor. And the testing is tailored specifically for the type of equipment that we get in to run a varnish. And there's a quick summary that our analyst would type up based on the overall findings and recommendations on the report. And here on the right is really the tests that we're doing. So all these individual tests are going to show up on this report, and it's up to the analyst really to correlate the data we get from these different tests. And what we have is essentially what we call our primary varnish indicators that they use to determine if there is a varnish issue. And those indicators would be the MPC analysis, which is the membrane patch colorimetry. We do a particle count comparison, which I'll talk about, and then we do a ultracentrifuge. So that is sort of the foundation of what we do to look at varnish potential. And it really should be a foundation for everybody out there looking at varnish. I mean, that should be the core testing you're getting done. So first, most of you are probably familiar with membrane patch colorimetry. It's what I call the granddaddy of varnish testing, and this goes back to the work of Dr. Sasaki. And really what we're doing is, and I should say this did become an official ASTM test. I think it was in December of 2012 or maybe January 2013. So there is a designation now. It is ASTM 7843, and it is a standard test that, if you're running it, any lab should be following the standard procedure. and it's really designed to identify soft contaminants associated with this oil degradation. And what you do is a portion of sample is treated with a solvent, as you can see from this picture, and it's poured through a membrane patch, and the insolubles are extracted from the oil and deposited on that patch. And if we remember our definition of varnish, it is colored. So the color of the patch is then analyzed with a spectrophotometer, and the results are reported as a delta E value on the lab color scale. And everybody's familiar with the number that you come up with for your MPC patch. And I believe we have a at-risk value of maybe 25 and a critical value of 33. So it's really measuring the darkness of the patch. And there's different factors, obviously, that can affect the outcome of this test. And two of them are particle count and the presence of water. You know, if there's an excessive amount of particulate contamination, the hard particles will be captured on the membrane patch as well as the varnish. So there's really, it's hard to distinguish hard from soft when you're pouring the oil through this patch. So as we talk further, that's one of the reasons why we run a dual particle count to try to isolate these particles. And also, if water contamination is present, the water does not readily pass through the membrane patch and tends sometimes to bead up on the patch. And you know, the patch on the right in this picture shows an example of, you know, that's what happens sometimes when we get water in the oil. It's not a nice clean patch, and it can affect the analysis when you're doing the spectrophotometer. And one of the reasons why the varnish analysis testing takes long is because of the ASTM procedure for running the MPC is that, you know, there's an incubation period for this test. So when we get a sample in, the first thing we have to do is put the sample in an oven for 24 hours. So the oil sits in an oven for 24 hours, and then it comes out of the oven, and then it sits at room temperature for 72 hours. So there's this, you know, essentially a 4 days of doing nothing with the sample before you can do an MPC patch. So, you know, oftentimes we may get a customer who says, hey, you know what, I got a varnish issue, I need a turnaround on this today. Well, you know, based on the testing that's going to be required, he's not going to be able to get a same-day turnaround on an MPC patch. It just isn't possible because of the way the test is run. You know, one of the things we do show on the report is what we call the LAB value, and this is sort of the color makeup of the final number that gets put on the report. And you know, there's a black-white value, a red-green value, a yellow-blue value, and we measure this, and based on the intensities of these different values, it can give our analysts some better sense of maybe how the varnish is being formulated. And I know when there's a, as it mentions here, a black color, a lot of times we could see it's a really dark black-gray patch, and oftentimes can be associated with some of the soot particles, or can also point to some micro-dieseling or even spark discharge in the oil. So it's another tool the analysts have to kind of give them a better idea of how the varnish is being formed. So I talked about particle count before, and it's an interesting, I guess, analysis we began about 2 years ago with the particle count, in that there's two different methodologies for running a particle count, and one is an optical particle count or laser particle count, and in this case the oil is passed through a laser or light beam, and anything present in the oil that interrupts that laser or light casts the shadow on a sensor on the other side of the light. So essentially anything that casts a shadow is counted as a particle. And this could include air bubbles, it can include water droplets, and I guess more importantly in this case, it can include soft contaminants such as varnish precursors. So we're running this, just think of this, we're running this optical particle counter that's going to be counting anything that casts a shadow on that sensor. And a lot of times those soft contaminants are casting shadows on the sensor. The optical particle counter, on the other hand, the pore blockage. What happens there is there's no light, there's no laser, the oil is passed through this calibrated mesh screen. And as the pores become blocked, the flow of oil decreases, and the instrument uses the decay and flow to calculate particle count. Now, if you can imagine this screen, and we have this pressure pushing the oil through the screen, what happens with the air bubbles, the water, and the soft contaminants, they get pushed through the screen. So they're not counted. All the pore blockage is counting are these hard particles that get caught up on the screen. So now you're going to have a particle count with hard particles and a particle count that counts everything. So if there's a big discrepancy between the two, you can either say, well, you got a lot of air bubbles, you got a lot of water, or you got a lot of soft contaminants. So usually what happens with the particle count when we're doing this is that we pick up this, you start to see a big disparity between the two values like you have on screen here. You know, the current sample here now is at 21/2018 for a laser, and the pore blockage is at 15/14/12. So something is in that oil that is causing that laser to count a lot more particles than the pore blockage. And typically it is associated with these soft contaminants. And that's why we run both tests. And you'll see if water is a problem, we run a Carl Fisher water as well, just to eliminate water as a potential interference here on this test. But this has given us pretty good correlation. You know, when you see the MPC value increase, you typically then start to see this particle count disparity between the pore blockage and the laser. So for us, it's a very good tool as another sort of affirmation that we do have a varnish issue. And then finally, the last primary indicator we use is the ultracentrifuge. And it's a pretty straightforward test. It's the oil is spun at a very high rate of speed. I believe it's about 17,000 RPM for about a half hour. And the higher molecular weight of these varnish particles will be forced to the bottom of the centrifuge tube. And the deposit then is compared on it's sort of like you would imagine a color chart. This is just a scale of 1 to 8 of intensity of this, what I call the bullet on the bottom of the centrifuge tube. So in this particular example, the one on the far right has a bullet, that little dark spot you see on the bottom of the tube of intensity of 1. As you start to move left, that intensity gets more, that bullet gets more intense to where you're already over to the far left, the current sample, that is a rated of a UC value of 6. And the scale again goes from 1 to 8. And the flag for us is a marginal condition is greater than, I think now we're using a greater than 5. So again, it's another tool we use to make sure that there is a varnish issue going on and that we're not going to miss it. When we started this 10 years ago, probably 9 years ago, when we came out with our first varnish report, all we were doing at the time was the MPC. And it just wasn't, I mean, we were reporting no problems with varnish, but our customers still were coming back to us and saying, you know what, you're saying negative varnish, maybe my MPC value was 1520, but I know I got varnish in the system. So there's something not right here. So that was part of the reason why we dug further and further into our varnish potential solution. So these are, what factors can affect this. Again, it's particle count, presence of water, fluid type. We often do these with phosphate ester fluids, which are found a lot of times in EHC systems in power plants in the turbines. And the phosphate esters will not spin out material unless the fluid is diluted due to the lower specific gravity. So a lot of times, because the EHC fluid has a lower specific gravity, it won't spin out the deposit like normal mineral oil. So in addition to the primary varnish indicators, which I've talked about, we've included some tests which can indicate a risk for varnish formation. And the first one I'd like to talk about is the ruler. The ruler's been around for a while, but it's probably, it became a, I guess, routine tool for us, at least, probably about 5-6 years ago. And what the ruler does is we're measuring anti-oxidation additives in the oil. And it uses what is called linear sweep voltammetry to test for the presence of additives in the oil. And you take some oil and a solvent is used to extract the antioxidants from the oil. And there's typically, you're looking at amines and phenols as the antioxidants in an oil. And each of these antioxidants will react at a different time and produce a different peak on the ruler graph. And what you do is by comparing the areas of peaks produced by the in-use oil or in-service oil to the peaks of a new virgin oil, it's possible to calculate the remaining useful life of the antioxidants. And as antioxidants become depleted, the ability to resist oxidation decreases, and again can be a precursor to a varnish problem. So if we're looking at this particular graph, and I'll just explain this real briefly, but in this example, the green graph here, the first peak would represent amines in the oil, and then the second green peak would represent phenols in the oil. And the green graph is the reference oil. So this would be a new oil that we'd have in our database, and that's what the additive pack looks like brand new. So then what you do is you take the used oil and run it through the ruler, and you're going to get two similar graphs, except they're going to be at a lower scale. And what you're doing is you're taking a measurement of the area underneath those two peaks and doing a little bit of subtraction to calculate percent remaining of each additive. So you do a subtraction of the first peak and you say, okay, I have this percent phenols remaining, and then you do the same on the peak to the right and you say, I have this much remaining of the phenols. And the way I like to explain this, because there is some complication associated with the ruler, but if you think of the phenols as the Gatorade for the amines, because the phenols are self-sacrificing additives. They're the ones that go first, and they get used up because they are re-energizing the amines in the fluid. So typically what you see happen is the phenols will be depleted first before the amines, and I think what we do is we'll flag the phenols when they get below 20% remaining life as a potential risk for varnish. So that's a quick summary of what goes on with the ruler. But this is a very good test for us. It's a very good look at looking at the additive pack in a turbine oil, hydraulic oil. You know, they're typically turbine oil is a rust and anti-oxidation oil, and if you're looking at the ICP metals, you're not going to see any sort of additive signature like you would on a EP oil or anywhere oil. So this is a good indication for us and a good tool we use to sort of qualitatively look at, you know, what oil, what turbine oil, what hydraulic oil is in the system. Next trivia question, because this is a question that comes up often that customers ask us, and it's really, you know, and I'm sure it's very common for you folks out there, is that you don't have one particular oil in a turbine, in a hydraulic unit. It could be mixed. You know, you may never completely change out a certain turbine oil and add a new turbine oil. You may do some sort of compatibility testing, realize that, you know what, I could do a bleed and feed and just add something new. So we get the question all the time, and it still can't, the ruler still can be done on mixtures of lubricants. And what the lab does is looks at what you think is the predominant lubricant as the baseline. And then what we're doing is trending that ruler analysis over time. So while it may not be perfect, it still gives us some idea of what sort of additive pack is in that oil. Another test you're going to find that is considered a risk indicator test that we do is just acid number. It's, you know, I'm sure most of you get it done routinely on your oil analysis, and this is just sort of it's what we would call a lagging indicator of a varnish issue, because usually you'll pick up some sort of oxidation occurring before you're going to start to see a spike in the acid number. But we do consider this an important test for varnish, and it does oftentimes show up as an increasing number as the oxidation or as the anti-oxidation additives deplete. And then, as I mentioned before, water can be a problem with some of the tests we run into. When you're looking at the MPC, you're looking at the ultracentrifuge, and even the particle count, it can adversely affect those tests, so we like to quantify the water. And obviously, when anybody who's had water in their system can sometimes detect it, but other times it's not so easily detected. And we don't just like to guess on the water, so we will quantify the sample with a Carl Fisher percentage of water just to help the analysts in their analysis. And again, this is just what the Carl Fisher looks like. It's just a test can quantify presence of water. And then finally, the last test we do is an FTIR spectroscopy, and it's a sort of an infrared signature of the oil. And we have set up some of our own FTIR modules that look at specifics in turbine oil that can give us different looks at degradation, oxidation, additive depletion, and which would be indicative of future varnish problems. And there's an art to interpreting these spectra, which our chemists are very good at. So the data that comes out in the report would look like this. We give you these indexing numbers and these different parameters. The new oil is baseline there in the gray, and then what we're doing is just trending these specific parameters that are represented as peaks on an infrared graph. And when we run an FTIR, an infrared beam is passed through the sample, and then the molecular features of interest will absorb the infrared energy at specific wavelengths. And these specific areas of the spectrum they're the ones that produce the parameters we're looking at. And these are trendable indexing numbers that we monitor over time for fluid health. And this will come up more as we go into a specific report. So I do get lengthy on this, but there's a report or two I would like to talk about as an example report. So that talks about the testing we do on our report. So if you look at, I had a few examples here. I don't know if we'll get to them all, but let's look at this first one, which is a gas turbine. So this is, probably 85–90% of the samples we get are from gas turbines. So this one, we flagged it as critical. So why is this critical? So let's take a look. So in this case, the MPC color value and particle count comparison indicate presence of degradation byproducts. So this is looks like a pretty straightforward analysis. As I scroll through it here and look at our primary varnish indicators, you can see here the MPC has gone, we move from right to left. So you're going from an MPC value of 7 to 26 to 39 to 37. So the last two have indicated a problem. We flagged 23 as being abnormal, and this obviously is showing some sort of abnormal wear. Critical limit is 33. So we would consider this a problem. So is there anything else to support the problem of a potential varnish issue? Or could this just be a lot of particles? How do you know it's just not a high particle count affecting the patch? Well, if you look at our particle count disparity here, our pore blockage particle count is pretty low. I mean, the current sample has a 15-13-9. I mean, that means that this isn't dirty. There's not a lot of hard particles, a lot of dirt affecting this sample. If you look at the optical, big number, big disparity going on here. So that disparity typically revolves around the water, the air bubbles, or soft contaminants. So there is some data here on the particle count to support a varnish issue. Further down, the centrifuge really isn't showing much yet. These particles aren't an issue as far as the centrifuge is concerned. It's going up a little bit. It's gone from 2 to 3, but nothing significant. And then as we move further down the ruler, you could see the first column shows the amines at 87% and the phenols at 27%. So there is some depletion going on, but not to a critical level yet. Once that gets to about under 20%, that will get flagged. Acid number is not an issue. No water in the sample, so it goes back to the particle count saying, well, there's probably are soft contaminants in there that are being captured by the laser that aren't being captured by the pore blockage. So good chance here. Looking at the FTIR, again, data shows good correlation to trend data. There's no significant fluid degradation. So that would be a complete report on this, and we go back and say, based on the MPC and the particle count correlation, looks like there is a problem you have with varnish. So it would have just probably arisen here because back here in March of 2014, really didn't see any MPC value of significance. So it's gone up over time, and that's the whole idea of doing a varnish analysis test. And quickly, I'll look at this one because I think this may have a opposite problem. So again, it's it's a gas turbine, and if we look down and see what the problems were, this time it's a UC value and a particle count comparison. So in this case, as we scroll down, you're going to look at the MPC and say, wow, if you were just doing the MPC, you'd probably walk away and say, I don't have a varnish issue. You know, I've gone from a 6 to an 8 to a 5 to 11, pretty good. Below alarm limit of 23, you know, it's never going to get flagged. Then you start to look at this particle count and you say, wait a minute, there looks to be some disparity between the pore blockage and the laser here that is rather significant. This would be like, for the analyst, an eye-opener saying, wait a minute, well, how could that be? How could it not be being caught on the MPC value when there is such a disparity? You go down to the ultracentrifuge and say, wow, significant problem here with varnish. This is probably one of the higher UC values I've seen of a 7. Rarely do you see a 7 or 8. Big problem. So we're capturing some sort of submicron particles in the centrifuge, but not in the MPC patch. So let's dig a little further. The ruler, okay, we're starting to see a real issue here with the additive pack. So virtually your antioxidation package, whatever is in here, is getting to a critical level, being depleted, now causing a potential oxidation issue with the oil. So we're going to dig deeper. No water, so it goes back to support our particle count issue. The FTIR. We look at the FTIR and it's really, you know, nothing significant. I don't really see any degradation going on here, nothing to raise a red flag. So what we do is when we have that big bullet in the ultracentrifuge, we will pull out that bullet. We'll take a syringe and try to isolate that material in the bottom of the centrifuge. And we call this deposit classification. It's sort of an additional test we do to try to figure out what is causing the varnish. So then our chemist will take this and they'll run it on a FTIR. Again, high-level stuff to look at the spectrum and try to get a fingerprint of what exactly is being pulled out of that oil in the ultracentrifuge. And when you look at this particular sample, what's being pulled out is formulation-derived additive. So it's an additive that's in that oil, and they know, based on their experience working with all sorts of different turbine oil, that this is PANA. PANA is an additive in a turbine oil, primarily, that oftentimes falls out of the oil and forms varnish. It's a big problem with PANA, but they could tell by looking at this signature on the FTIR spectrum that that is what's in the UC value or that is what is in the ultracentrifuge at the bottom of that. So it's just further analysis that gives them an idea to say, you know what, yeah, the ruler showed that your additive pack is being depleted, it's starting to fall out, and it's causing this varnish issue. So something needs to be done ASAP on this particular system. So that gives you some sense of, and I should say this is, I'm not an expert. I have not been involved in the analysis of these varnish testing in a number of years, but I do know that PANA, this is pretty typical of PANA in that it will not show up on the MPC patch here because it is a lot lighter and doesn't fall out of solution like some additives do, but it does come out of the ultracentrifuge. So it's kind of a unique problem we have with when we discover PANA as a varnish problem. So that is the, I guess, 50-minute view of varnish and what you should do to kind of stop varnish from causing a lot of problems in your systems. I think understanding of varnish and how to monitor it continues to grow. You know, we're by no means done doing further research into varnish. It seems like every year or two we find something new to add to our varnish report. And you know, the whole idea is to help you guys try to figure out a varnish issue sooner rather than later. So I want to thank everybody for joining us today. I hope you find the information useful. And if you have any questions or need answers to problems you may have, feel free to email me or call me. And I just want to thank you for your attention and time. I really appreciate it. Hope everyone has a good week.
All right, Mike, can you hear me?
Yes.
All right, everyone, thank you for that presentation, and everyone, thank you for joining us. Later on this afternoon, you will receive an email with a link to a survey and also a link to the recording. And if you have any questions, please feel free to let us know. Thanks again.